So let's break it down and take a look at the function if we're plugging in specific values for x. So I made a t-chart here. I'm going to start with x when it's negative 10. So I'm going to plug that into the function there. I have the 1 over x minus 1. So I'm going to plug it in. I'm going to get 1 over the negative 10. Take away the 1. That's, of course, 1 over negative 11. All right. So that comes out to be about negative 0.09. So I'm going to write that down. Then I'm going to go to the next one. I got a 1 over the negative 1 minus 1. So we're going to have 1 over negative 2. So it's going to be negative 1/2 for that one. Then we're going to have, plugging in the 0, we're going to have 1 over 0 minus 1. So that's really just negative 1. Then putting in 1/2 for x, it comes out to be, now notice it's 1 over 1/2 minus 1. So in the denominator we have 1/2 minus 1. So that's negative 1/2. So we're really doing 1 divided by negative 1/2. So let's look at, I wanted to break this down and look at this as far as when you're dividing by a fraction. So in the denominator it's negative 1/2. So remember that when we're dividing by a fraction, sometimes people call it the keep, change, flip rule. In other words, we keep what's on the numerator, the 1, and right now say I have it written as 1 divided by the negative 1/2. I'm going to keep the 1. So I'm going to write 1, and then change the division sign to a multiplication sign, so 1 times, and then I flip the negative 1/2 to a negative 2. So that's when you're dividing by a fraction, you actually get a bigger number. So that comes out to be, right there, negative 2. Then let's putting in really close to, I'm going to put in 0.99. Okay, so the reason, you'll see why I'm doing this in a second. I'm going to do 0.99 for x, so 1 over 0.99 minus 1. So in the denominator, we have a very small amount. We have still 1 on the top. We're going to have negative 0.01 in the denominator. So what is that really, negative 0.01? Well, that is negative 1/100th, because it's 0.01. So really, I'm doing 1 divided by that negative 1/100th. Okay? So I'm going to, it's a similar thing what I just did. We're going to do the keep, change, flip here. So I'm going to do the 1 times, and I'm going to flip the negative 100 to be negative 100 over 1. So that comes out to be negative 100. So you see when you're dividing by that, when you have put the 0.99 in for x, you end up with the function being worth a negative 100, and that's the y-coordinate. Putting in 1, what happens when I put in 1 to this function for the x value is that I can't do that really because I would end up with 0 in the denominator, and anything 0 in the denominator is undefined. You can't have that. So I'm just going to put in for my t-chart, I'm going to put in that just a scratch here, mark, because you can't have that. Okay, so it's not going to exist on the graph. And I'll show you what that turns up as on the graph in a moment. So then I'm plugging in a few more where I've got 1.01 on the bottom, and then that's going to come out to be, again, when you do this, you're really going to be dividing by 0.01, and that comes out to be 1. And then finally I plug in 2 for x, it gets 1 over 1, so 1. I'm going to take these values and show you where they show up on the graph for this function right here. So let me just quickly sketch it here. Let's say we have this is a quick coordinate plane, and I go just like this, and I'm just going to sketch these. So when I have the first one here at negative 10, when x is way over here at negative 10, this is very close to 0, but slightly below the x-axis. So that point would be right about here. Now the next thing when I do is I go to the negative 1 here, so that's much closer to the, that's right here, much closer to the y-axis. There's a negative 1, and so let me get that out of the way there. So this is a negative 1 right there. When I'm plugging in plug into the function, I get that come out to be really close to 0, but not as close as this to the x-axis, a little bit farther away. So maybe about here. Again, if this is like, if I say that that's about negative 1, I'll do about a negative 2 here. So again, if I have this right here, if when x is 0, I have negative 1 for the y-coordinate, so that would be right here. Now when I get to 1/2, so let's review this again. So on these graphs, whatever function you have, let's say you have this and you have x plus 2, what I want to do is I want to look at, the first thing you want to do is what makes this, you set this denominator equal to 0. Or actually you just say the denominator can never equal 0, right? So x plus 2 cannot equal 0. So really solving that, I say that x can never equal negative 2. In fact, if they're asking you for the domain, which they often do, you would say x can be any value from negative infinity up to, but not including, negative 2. Then we would do union, and it would skip that negative 2 and go on to infinity. So, and so in these, what that looks like is that is going to be that vertical asymptote at x equals negative 2. So that's one thing you want to identify when you do these. So that's the vertical asymptotes. Now, you may have two of them. So let's say you have a function, let's call it g of x, where you might have, the number on top doesn't really matter right now. So let's say it came out to be that this was x squared minus 9 in the denominator. Well, I need to find out what makes the denominator 0. So you could either say, okay, x squared minus 9 cannot equal 0. And you could do it this way, x squared cannot equal 9, and then taking the square root of both sides, I get plus or minus 3 over here. X cannot equal plus or minus 3. So I actually have two vertical asymptotes there. But factoring the bottom is key to find out what... So there's another way I could do this is I could factor this. I could say x minus 9 cannot equal 0. You could do difference of squares, x plus 3, x minus 3. And then you can see that x can't be 3 or x can't be negative 3. So that's how you're dealing with finding out what makes the denominator 0. So now I want to look at something where we've got a horizontal asymptote. Okay, so horizontal asymptote is when, if you have a graph that looks something like this, and let's say my graph looks like, kind of like I just did, but it looks like this, okay, and I have a vertical asymptote here, and then this kind of goes like right about here, this side of the graph. And you'll notice that here I have, make this a little bit higher. So let's say this kind of comes in like this, okay? So what I'm doing here is I'm saying, oh, there is a horizontal asymptote. Okay, so again, what is an asymptote? An asymptote is when your graph gets, let's say you're right here, all right, and you're going this way following the graph. Notice I'm going toward this line right here, that asymptote. But I think of it as a cliff. I'm heading toward that cliff, and I have to turn and not go over that cliff, but I'll get closer and closer to that cliff, approach it, but I will never actually touch it. So that's a horizontal asymptote, is right, this dotted line horizontally. So let's say that on my y-axis that this was x equals 1, and this is x equals 2, and x equals 3, and x equals 4, and so on. So right here, when y equals, so when y is 2, y is 3, y is 4, y is 1. So I have a horizontal asymptote right here through where y is equal to 2. That means that the equation for my horizontal asymptote is going to be y is equal to 2. Okay, so that's what a horizontal asymptote would look like. So how might we see that in the equation? All right, so there's a couple things you need to know here. When I really have three rules. So I'll just go to a clean page here. So when I have a function, let's say we say f of x is equal to, back before I was saying, oh, maybe it was 7 over something like that, okay? We need to talk about what's called a degree, the degree of a function. So you may have run across this before, it's very important. The degree would be, let's give you an example. So when we're talking about maybe a line, say y equals 3x plus 7, what is the highest exponent of the x? So right now there's only one x, right? There's only an x in one place. So what is the exponent or the power for that x? Well, of course, it's a 1. So we would call that a first degree function. But let's say I have, talking about a parabola, something like 2x squared minus 4, doesn't really matter. That exponent is a 2. And so even if I had gone and said, maybe if I just changed this and had this 4x plus 1, still the highest exponent of the x value is the 2. So that we would call a second degree. All right, and then if you had anything, say x cubed, and it doesn't really matter what the rest of it is, this would be your third degree, right? So we need to know that, and the reason we need to know that is because we need to compare the degrees in the numerator. I want to look at the degree in the numerator, and then I want to look at the degree in the denominator, and I'm going to compare them. So there's going to be three things that you can get. Something like this, where, like I was doing, where I have this over that, okay? Now, what is the degree in the numerator? Well, since there's no x, that means we're just going to call it the degree is 0. Now, in the denominator, of course, you have x to the first, so the degree equals 1, all right? So in this case, the degree is bigger on bottom. So here's a little kind of memory technique that some teachers use. The degree is bigger on the bottom. And so what we're going to do is this is always going to come out to be a horizontal asymptote of y equals 0. All right, so if this was my x-axis right here, this would be the asymptote. You know, you might have the graph might be something like we were looking at before, where it comes in close there, and maybe like this. Okay, so that is when you have bigger on bottom. Now notice, this starts with a B, O, B, and then we get y equals 0. So a silly but sometimes helpful memory technique is to use the acronym B, O, B, and then the 0 or O. BOBO. Bigger on bottom, 0. Okay, sometimes people call us like the clowns or something. Okay, so that's for bigger on bottom. What about if we have them the same? So if we have, what if it had been 7x over an x minus 3? Or we had maybe an x squared plus 1 over 4x squared minus 7x, or something like that. Okay, notice how they're the same. Okay, so this is a first degree, this is a first degree. Here's a second degree, here's a second degree. So when they're the same on top and bottom, or just say the same degree, okay, you're going to do what's called the coefficients. What I mean is you're going to look at the coefficients of the leading terms. So what are the coefficients right here? Well, example, this one, the coefficient of x is 7, and since there's no number written here, it's a 1. Here, the coefficient in this one is a 1, and then this is a 4. So your horizontal asymptote is, for instance, in this one, would be y equals 7 over 1, or y equals 7. That's the horizontal line. So let's say it was up here, and this was a 7, there would be a horizontal line there. This one right here, where I have the 1 over 4, the horizontal asymptote would be y equals 1/4. And then I would draw a horizontal line through 1/4. So if we have the same coefficients, if we have the same degrees, we use the coefficients. So SACO could be SACO, to remember for that one. Same, use the coefficients. And then the last situation will be, and I'll just put it up here, if you have bigger on top. So if I have a bigger on top, would look something like if you had f of x maybe equals 7x squared minus 5x plus 1. Again, I only care about the leading term, and this could have been maybe 3x minus 1. Now I have the degree. Notice here is a 2, and here is just a 1, so I have bigger on top. Bigger on top. So bigger on top, you're going to end up with no horizontal asymptote. So bigger, we're going to use the B again. This is bigger on top this time, though. We're going to put, there is none. There's none. there's no horizontal asymptote. So the clown name for this, I don't know what they call it. They sound like clowns. That's why they say this technique. B-O-T, no. So bot, no. Bigger on top, no horizontal asymptote. So again, the x, the number in the denominator, whatever you get in the denominator, that's going to determine your vertical asymptotes, whatever makes it 0. And then these three rules, not necessarily in any order, but bigger on top, bigger on bottom, or same. So that's going to be the rules for finding this horizontal asymptotes. So let's look at this again. So let's say I have this function right here where I have f of x equals, I have 3x squared minus 6x, and this is going to be over x squared minus 3x plus 2. And I want to know what I do with this. Well, the first thing you want to do is you're going to want to know what makes the denominator 0. All right, so what makes the denominator 0? I want to factor that. So we're going to factor this x and an x. It's got to multiply to positive 2, multiply to, or add to negative 3, so I'm going to minus 2 minus 1. So right now I know that in my denominator, x cannot equal a 2, because that'll make this part 0, and x can also not equal a 1. So I know my vertical asymptotes are at x equals 2 and x equals 1. Then as far as my horizontal asymptote, well, what do I have? I have the same degree up here as I do here. So same coefficients. SACO, same coefficients. So my horizontal, so this is my vertical. Okay, so my horizontal asymptote is going to be, using the coefficients, I have a 3 here, and then this is a 1. So y equals 3 over 1, or just 3. That's going to be my horizontal asymptote. So I have identified some important things there. From there, you're going to build on this and be able to sketch these and add find the y-intercepts, the x-intercepts, and we'll build on it from there. But that's vertical asymptotes and horizontal asymptotes. Those are the key features in doing these rational functions.